In this video, we're going to talk about corrosion and its prevention. Now, corrosion is just the destruction of materials, usually metal, by chemical reactions with substances, which is usually oxygen and water in the environment. Okay, so if you leave something outside, there's oxygen, there's water, it's going to start corroding. Now, a specific form of corrosion that we all know about is rust, because bikes rust, for example, chains, when you have them go all kind of orangey brown. Now, if that is the case, okay, rust is a specific corrosion of iron. That means iron is added to oxygen and water, and we make this thing called hydrated iron 3 oxide. Now, hopefully from the start of your course, you know what iron 3 oxide is, so maybe stop the video and try and write out what iron 3 oxide is. But you need three things to make this rust happen quickly, okay? And that's why if you live by the sea, you've got lots of water. Obviously, everyone has lots of oxygen, but lots of water, and you get loads of rust if you're living right by the sea. Now, the balanced equation is here. Iron plus oxygen plus water goes to this iron 3 oxide. So there, if you had to stop the video, there it is, iron 3 oxide. With the waters bonded to it. This dot here just means the waters are bonded to it. Now, the colour is this orange browny colour. And that's all you really need to know about rust in terms of the chemical equation and the word equation. We're now going to move on to do an experiment to test why rust forms. We know rust forms because of water and oxygen, but we need to prove that using a test. So we choose an iron nail and we do our first test tube. We're going to do 5 test tubes in the end, okay? And you can work out before I talk what each one of those are if you want. So stop the video and try and work it out. Okay, but this one is open to oxygen and water because it's open to the environment, and in the environment is moisture. So we want to see over, for example, a few days or something like that, what happens to this nail. And we know probably nothing's going to happen to the nail because nails don't tend to rust if you just leave them in the air. If you then go to the next one, we need to isolate which one. We need to find out which one causes the rust. So therefore, let's isolate one of them. So let's make it in this one that we only have oxygen and no water. And we do that through a drying agent. So the drying agent bonds to the water and removes it and sticks it down here, which means it's bonded. It can't react with anything else. It's bonded to this drying agent, which means we only have oxygen in here. And we put a bung on just to make sure there's only a set amount of air in because this drying agent only works for a limited amount of air. Okay, put the bung on, and this is exposed to O2 in the air, no water whatsoever. Next one, put it in oil. That prevents all the water and all the oxygen from getting to the nail. So totally nothing reacting from all oxygen and water with this nail. Just oxygen and water, but not a lot of water. The next one is when we put it in water. Okay, so we've isolated the oxygen, we've isolated the water, and we've made sure there's no oxygen and no water. So you can have a prediction and think, what do you think this will look like? Now, just to add one on, because we know if you're by the sea, you get a lot of rust in different places. Okay, we put one with a salty solution, so sodium chloride and H2O. Now, I have a prediction. Which one do you think, over a few days, will go rusty? Okay, so if we look here, we can see that our 2 tubes, here and here, have gone rusty. That has not gone rusty at all. Okay. That has not gone rusty, and that has not gone rusty. So what it's saying is, basically, with the little amount of water that you've got in the air, there's not enough to get this going. There's no water there, so this doesn't work. There's no water or oxygen there, so this doesn't work. There is water, so it does get rusty. Okay, so there will be, for example, enough to get it rusty, but it speeds up and it gets even more rustier using that. Okay, remember there is a little bit of oxygen dissolved in water, so therefore it still proves that it works better with the oxygen. But water, okay, is really, really important to make things rust, as you can see from this. So if I take this and then put this above a nice picture to remind you, as you can see, very rusty underneath the water here because of that salt and that water. So both air and water are needed and are necessary for iron to rust. Okay, salt speeds up the process, And if you live by the sea, it means iron-based materials are much more likely to rust and rust quickly. We're now going to go through all the different methods of the prevention of corrosion. So you have internal combustion engines, much like this, and things like that. And this is more like a jet engine and stuff like that. But you can see here that you've got lots of moving parts. Now you normally have oil and grease and things like that around those to lubricate them, but you also do it as a type of barrier protection. So that provides a barrier between the oxygen and the water and the metal itself, so you don't get the corrosion. And that's known as greasing, okay? But again, the same process happens if you put oil in an engine. So, if that's the case, another version is painting. So here we have a gate. Normally you paint the gate a nice colour that you want it, but actually it's there also to protect it from the oxygen and the water and prevent it corroding. Now, if that's the case, the last one we're going to talk about in this section is electroplating. So electroplating can be done with, for example, a ring, and we've got a fairly cheap looking ring here with a big with a big stone on top. But you can see here this could be any cheap metal or something like that, and this could be plastic. So you can make this look a little bit more fancy, and you can do it in lots of other different ways as well by electroplating, which is coating the cheap metal in a more expensive metal, which means you use less of that. So if we move that out of the way, okay, and then we say, right, okay, using the metal that's to be coated as the cathode. So the cathode is negative, so the positive metal ion is attracted to the negative electrode. Remember, all metals are positive ions. It's then attracted to the negative electrode, and you make the thing you want to be coated the negative electrode. So in this case, we would make the ring the negative electrode, so the metal ions would flow towards it and then gain electrons and then coat the metal object. Now, that metal coats the object and provides some form of protection in terms of sacrificial or just protection. So sacrificial means it will rub away over time and it sacrifices itself to protect the other one, and then you'd have to just recoat it, for example. Now, it is cheaper, as I've said, because the less expensive metal is used as the main metal. Okay, so cheaper. And then you use the more expensive, for example, gold-plated rings. Okay, so less gold is used, and so overall, the whole thing is cheaper. We're now going to talk about a couple of different elements with specific examples. And the first is aluminium. So aluminium is a bit of a special case because aluminium is one of the most abundant metals in the world. It's used for lots and lots and lots of things, but actually it's highly reactive. Okay, and we'll show you that in a second. But what actually happens is these are oxygen atoms, O2, and they react with the aluminium to create aluminium oxide. Now, the aluminium oxide is a protective layer, but before we talk about what that means, we'll show you the true reactivity of aluminium. Now, if that is the case, here we have aluminium, you see it just here, and this is bromine. And the bromine strips off all of the aluminium oxide, leaving the aluminium underneath. And then it shows you the true reactivity. This is a really cool reaction, right? Okay, so, and it shows you all of that. And you can see how reactive it is. I wouldn't want to put my hand here, for example. Okay, and this was done in a fume cupboard. So that shows you how reactive the aluminium is. Okay, but you don't see that because otherwise you wouldn't coat your sandwiches in aluminium foil. You wouldn't have aluminium everywhere, and you have aluminium everywhere because there's that oxide layer, which is highly unreactive, which is just coating it. Now, that oxide layer is really thin, okay? And it makes it resistant to corrosion. So it's so thin you can't even see it. So that's why the aluminium just looks like aluminium to you, but it's not. It's coated because of that reaction over there, which protects it. Now, the unreactive stops the metal from reacting with oxygen any further. So all the metal underneath is safe, okay? And remember, the aluminium is high up in the reactivity series, but seems unreactive just because of that aluminium oxide coating. So it's a bit of a weird one where it's really reactive, but actually because of that coating, it's saved from being corroded, and actually is really safe to put on your food and such and forth and store your food in. Our final example is galvanization, which is a specific example where you coat a metal object with zinc. Now, zinc is not very reactive in normal temperatures with oxygen, water and things like that, so it's not very reactive. Okay, so it's a good way of coating. Now, just before I do that, look at this reactivity series again. Just remind you that aluminium has that aluminium oxide coating that protects it, okay, because aluminium is really reactive. And then you've got your zinc and you've got your iron here. So we're going to take this iron, we're going to coat it in zinc. So metals such as iron can be covered in a layer of zinc, and this is called galvanization. Okay, and that's an example of sacrificial protection. So we're sacrificing another metal to save the metal underneath, to stop the metal underneath from reacting. As you can see, zinc is more reactive than iron. So let's look at it happening. They just dip it into the molten zinc, that's all they do, and then they bring it back out, and it will be a galvanized piece of iron. That might be used for railings and things like that you have in houses that go outside and stuff like that. You'll see it everywhere. If you have a look, it's got a certain look and feel, okay, and it will be there all the time. And you can see zinc is more reactive than iron. So just to finish this off, the more reactive metal reacts instead, hence sacrificing itself to protect the other. An example of this is sacrificial protection.